So let us begin with the first topic that we would have to address. That would be the definition of a signal. Again, I am assuming that this is a topic that you would have already addressed, and this is happens to be a speech sample, a segment of a speech sample, a speech signal. We say it's S of t. So on the y-axis we call it amplitude. So this is S of t, and on the x-axis is time. Okay, I am sure you would have looked at many such signals, and so when we look at this signal S of t, this S of t is the signal that we are interested in. T is in this case the time index. We call that as the independent variable. So a signal is a function of an independent variable. It could be time, it could be the x dimension or the y dimension. So basically a signal is a function a function of one or more independent variables. A signal is of interest because it carries information. Okay, a signal is an information bearing quantity. So we have this as an example. This is a speech signal. The duration of the speech signal happens to be 32 milliseconds, just a very small segment of speech, and we are representing it in this form. Now, this is a case where S of t is a one-dimensional signal because there is only one independent variable. It is a one-dimensional signal. Now, if you had a color photograph, okay, the color photograph in the signal processing inside of the processor will be, so a color photograph will be represented by three functions. So a color photograph can be represented in terms of the red information x comma y. So I have a color photograph, and this is the x dimension, this is the y dimension. So basically the pixel information from each of those. So this is the red color information. Similarly, we can have the green color information. I should probably use the green color for this, and then we have the blue. So the three primary colors. So this is a function of two dimensions. Again, x and y are the independent variables, and you have the intensities of these three different colors. Now, you can have more than two dimensions also. For example, if you had a video, then you would have the red information, x and y, and time. Right? As time progresses, you have different frames of information, and similarly you would have the green x, y, and t, and the blue x, y, and t. Okay, so so I hope you are now comfortable with the notion of a signal being an information bearing quantity. It's a function of one or more independent variables, and this is what we are interested in studying. So the signal S of t in this particular case depends on an independent variable t, which is a continuous varying function. T can take on any value. It can take 0.1, 0.11, 111. It can take on any value. So it is a continuous variable. It is a continuous variable. Okay, so this is exactly what you would have studied in this course on signals and systems, and this we represent by saying t belongs to the set of real numbers R. This means it is on the real axis, it can take on any value. It is a continuous variable. Now, as I mentioned, our focus will be to quickly move from the continuous time to the discrete time. So let us take a specific example, and we will look at how we will study this particular. So let us take, this is an example. Consider a continuous time signal xa of t, which is e power minus t u of t. Okay, I am sure you are familiar that this would be this is x. If I were to plot xa of t as a function of t, this would be a decaying exponential. Okay, this is e power minus t starting at value of 1 and then decaying, and it has nothing in the negative, so starting at 0, and because of this u of t, there is no signal for negative t, it exists only for the positive time index. Now, if I were to ask you to take this signal xa of t and evaluate it at periodic intervals. So, evaluate it at time t equal to 0, at time t equal to Ts, at time t equal to 2Ts. So, this is Ts, 2Ts and so on, okay, 3Ts. So, this is what we refer to as the process of sampling, okay, sampling process. So, xa of t evaluated at t equal to nTs, where n can be 0, plus minus 1, plus minus 2, all any index. Basically, it is an integer value. Now, once you have done that, you do not have a continuous function, but you have the value evaluated at each of those specific instances of time. Now, that is what we refer to as the discrete time signal. So, for example, this is the value of the function x at time n equal to 0. This is at the time at n equal to 1 Ts, but I represent it as x of 1. So, this is at sampling xa at 0, this is sampling xa at Ts, I call it as x of 1, then this is xa of 2 Ts and so on. So, basically this is the process of sampling that we and what happens as a result of sampling is that you now get a sequence of real numbers. If xa was x of t was xa of t was a real valued sequence, now you have a sequence which has xa of x of 0, x of 1, x of 2, and you can also have x of minus 1, x of minus 2 and so on. A waveform became a sequence of numbers. Okay, that is the process of sampling and how we represent that. So, we can write down saying this discrete time signal x of n is a signal that has got a value at 0, value at 1, value at 2 and so on, and minus 1. So, basically it is a sequence of numbers. It can go from infinity to infinity basically, but it's a sequence of numbers. It is not a waveform. So, a few more points to note down in this context. So, discrete time signals, I will use dt for discrete time from now on for the rest of the course. That is our notation. Discrete time signals will be a sequence of numbers always, sequence of numbers. Okay, so if I were to ask you, is this a discrete time, does this qualify as a discrete time signal? I give you a sequence of numbers, there is 0.9, minus 0.2, 2.2, 1.1, minus 3.7, dot dot dot. Is this a discrete time signal? Yes. Do we have all the information? No, because we don't know the time index. So, one of the things that you would have to have for this sequence is to know which corresponds to the 0 index. So, basically from there you can count plus 1, plus 2, plus 3, minus 1, minus 2. So, an arrow is always indicated to show this is index 0. Okay, so then this becomes x of 0, this sample becomes x of 1, this sample becomes x of minus 1, then you have x of 2 and so on. So, that is how we would use, that is the notation that we would use for a discrete time signal. Okay. So, the representation of a discrete time signal is within curly brackets x of n. This basically means that you are talking about a discrete time signal. These are square brackets, note, compared to the curved brackets for a continuous time signal. So, we would always use square brackets for a discrete time signal. Now, x of n, just like in the case of the continuous time signal, can either be real or complex. So, we say that x of n belongs to the set of complex numbers, and a special case or a subset is the case of real numbers. Special case is the subset of real numbers. Real numbers indicated by R. So, now we are also going to mention that a discrete time signal x of n is defined only for n value of integer values. Okay, defined only for integer values of n element of z. Okay, this is the set of all negative and positive integers, set of integers. Okay, and please make sure that we also emphasize that a discrete time signal x of n is undefined if you are looking at any value which is not an integer, if n is not an element of z. Okay. So, for example, I have x of 0, this is 0, index 0, this is x of 0 at a height of 1, and I have x of 1 at a height of 0.5. Okay, it is a discrete time signal with just two non-zero values. Now, if I were to ask you what is x of 1.5, you cannot say, it is somewhere in between 1 and 0.5. Okay, no, this is not valid. It is not defined for intermediate values. It is only defined for integer values. So, again, very often we sometimes may say, well, it's somewhere in between. We cannot. It is not defined. It's defined for 0. It is defined for 1. Anything in between, not defined. Okay. Again, so that we are consistent in our representation of the signal. So, how did we go from a continuous time signal to a discrete time signal? Okay, so this is from continuous time to discrete time. How did we go from here to here? It is through a process called sampling. Okay, and to be very precise, it should be called as uniform sampling. And what is uniform sampling? We said that we will take xa of t, the continuous time signal, and evaluate it at uniformly spaced points on the time axis nts, and these points we will denote as the sequence x of n, sequence of values x of n. And Ts is defined as the sampling period, and 1 over Ts is called the sampling frequency. Okay. And if we denote the sampling period in seconds, the sampling frequency will be in hertz. So, again, that is how you would define the units for each of those quantities. Okay. And we also have a important result that we will be studying as part of week 3, but let me just state it for completeness now. When you go from continuous time to discrete time via uniform sampling, now you may think that, okay, I did not retain the entire waveform, I only retained the value of the waveform at certain points in time. Okay, is there a loss of information? Loss of information. Okay, very valid question. This is something that we must always answer, saying that when you went from continuous time to discrete time, did you lose any information? And the proof of saying that I did not lose any information is to say that I can always, if I can reconstruct the continuous time signal one more time, then this is a guarantee that there is no loss of information. Only when there is no loss of information can you go in the backward direction. Okay, and what is the way by which we guarantee the fact that there will not be any loss of information? That is called the Nyquist sampling theorem. We will study this in more detail, but again, this is something that just for you to be familiar with. It's called the Nyquist sampling theorem, and this Nyquist sampling theorem gives you a necessary and sufficient condition to ensure that there is no loss of information. That is, if you satisfy Nyquist sampling theorem, you can go from continuous time to discrete time and discrete time back to continuous time. So basically, this will guarantee that if you satisfy, if Nyquist sampling theorem is satisfied, then there is no loss of information. There is no loss of information in the discrete time signal, which is obtained, no loss of information in the discrete time signal. Okay. Now, this is one important element, and I just wanted to encourage you to keep this picture in mind, that we had a speech signal, we sampled it, and did we lose any information? The question goes back to saying, okay, did we satisfy the Nyquist sampling theorem, which we will study. So, the speech signal that we had, now I want to apply the sampling theorem. Okay, the sampling theorem. So, if I were to look at this, this is the same speech signal. This is S of t, the speech signal. This and the Nyquist sampling theorem. Nyquist sampling theorem in this particular case says that your sampling frequency Fs equal to 1 over Ts must be greater than or equal to 8 kilohertz. Okay. This is the same as saying you must sample at least at 8,000 samples per second. Samples per second. Okay, and so basically this is what we want to recognize. Okay, so now if it is 8,000 samples per second, then in 32 milliseconds, that is less than so in 1 millisecond. So this is the same as saying 8 samples per millisecond. 8 samples per millisecond. So 32 milliseconds will give us 256 samples. Okay, so this is 32 into 8, which is 256 samples. Okay, and you can start numbering them at 0, 1, 2 and so on, all the way up to 255. That your continuous time had a t as a variable. This one has got n as the index, and we will denote it as n, remember, square brackets of n. That will be the representation of the sampled signal. Okay. And one of the most powerful reasons or one of the advantages of signal processing compared to the continuous time signal is in the storage and reproduction of the signal. Okay. Now, if you were to store this continuous time waveform on a magnetic tape or on a audio tape, then with time it will degrade and then you will not be able to reproduce the original signal. Whereas if it is a sequence of numbers, no matter how many years has gone by, you can always recover the original signal by looking at a process of number. So this is why a compact disc can be used for many years. you can recover the information because it is not stored as a waveform, but it is stored as samples, and therefore a compact disc can reproduce the signal, the audio signal, music signal, whatever you have recorded on it. It can reproduce it even after 20 years. It absolutely no problem. So just for your interest, the compact disc stores the audio signal according to Nyquist sampling. It looks at Nyquist sampling rate and over satisfies. Okay, and we will look at why you would want to over satisfy, no, not the minimum, but more than the minimum, and does a sampling at 44.1 kilosamples per second, kilohertz sampling rate. That means 44,100 samples per second is the rate at which the CD signal will be played back. And one of the reasons is when you do oversampling, you can have more high fidelity representation of the signal, and that is why a CD quality or audio signal is of extremely high quality. Okay, and this is so you start to see how DSP plays an important role. Now, maybe this is also a good time to sort of say why some book, if you go back and look at the textbooks, the one on the left says discrete time signal processing. Okay, on the right hand side it says digital signal processing. Now, we often say DSP. Now, is there a difference? Why does one person call it DTSP and the other one as DSP? Again, it's a terminology, but it's sort of interesting for you to know. In the context of DSP, okay, time will always be discrete valued. Discrete valued. So, discrete time signal processing is a correct terminology. Okay. Now, what about digital signal processing? Now, we call it a digital signal under the following conditions. Supposing you had a continuous time waveform, we sampled this signal according to our sampling criterion, we got a discrete time signal, x of n. Okay, if this is x a of t, we sampled it and got a discrete time signal. Okay. Now, if you represent the signal with infinite precision, then it will remain as a infinite precision discrete time signal. On the other hand, if I have only a finite number of bits, I have to quantize these bits, quantize these samples to a specific number of bits. So, in which case I do not have infinite precision, but I have finite precision. Okay, finite precision. Then we say that it is discrete in time, discrete in amplitude. Discrete in time, infinite in amplitude, infinite precision amplitude. Okay, this we would call as a discrete time signal. On the other hand, if I have a signal that is discrete in time and discrete in amplitude, okay, then it becomes a digital signal. Okay, so again, not a big difference. We can always call the signals that we are working with as digital signals, but the correct representation, since we are not talking about quantization, we are going to, most of the time we are going to be talking about representing the with full precision. So, discrete in time and discrete in amplitude. Discrete in amplitude. Okay, that means you have quantized the signal to 8 bits, 12 bits, 16 bits, whatever the precision that you have. This becomes a digital signal. Okay, but what we are going to be developing are algorithms that can work with discrete time signals. Whether you have infinite precision or finite precision does not matter. The same algorithms. So, for example, if you say I want to describe a linear time invariant system, it is through a impulse response. That impulse response is a discrete time impulse response. It's a representation of a discrete time system. So, therefore, whether quantization is involved or not does not matter. So, which title is correct? I would say both are correct. One of them is focusing on the fact that I'm going to deal with discrete time signals, but infinite precision. This one says you can also apply it to quantized signals. Again, both are correct. Both are talking about algorithms and techniques that can be applied in both contexts. I hope you are comfortable with this representation. Okay, now that we have developed a basic representation of the discrete time signals, I would like you to quickly review before the next session the basic signals that we have in continuous time. Basic signals that we will have in continuous time. Okay, what are some of them? One will be the unit step function. The second one will be a Dirac delta or a delta function. Dirac delta. So, this will be u of t. This will be delta of t. Look at all the different types of signals that we we have worked with. An exponential sequence of the form e power minus at, okay, and causal sequences where you have a e power minus at u of t. U of t will ensure that you only have non-zero values of the signal of time. Then look at sinusoids, signals of the form a e power j omega t. This is a complex sinusoid. Or you can talk about a real valued sinusoid, which will be b sine omega t plus phi, or b cosine omega t plus phi. These are sinusoids. Okay. What we would like to do is quickly look at the counterparts that we will have for each of these signals. And we will then develop these signals from the discrete time domain perspective. Again, very important that we are able to completely move over to the discrete time domain and then try to look at the representation of signals in the discrete time. Okay, so a quick run through of what we have covered so far. Our focus is to transition from the continuous time representation of signals and systems to a discrete time representation. We will look at the aspects of how we take a continuous time signal and obtain a discrete time signal through the process of sampling. That, and how do we represent a discrete time sequence as a sequence of numbers which all have an index n, which has to be an integer. Only integer values are allowed. That's the basic definition of a continuous time signal. We also said that the Nyquist sampling theorem affirms for us that we can go from continuous time to discrete time and be able to reconstruct the original signal. So again, we have the basic framework. We can also, before we conclude today's session, we have another form of discrete time signals. These are signals which are inherently discrete in time. So, for example, if you have a thermometer which measures the temperature once in every hour, you have some process that is running, let's say a steel mill, and you are taking the temperature every hour of the system. So this is a sequence of numbers which, let's say, you start at 1 a.m. in the morning, then 2 a.m., So this is at 1 a.m., this is at 2 a.m. you measured, and so on. Okay, so this is a sequence of numbers. So notice that this is a discrete time sequence which occurred as a discrete time sequence. It did not come from a continuous time which was sampled. So we can have signals which are inherently discrete, or we can talk about signals which are continuous in their origin but have been transformed into the discrete time domain, so that now we can apply the discrete time signal processing tools and techniques so that we can take full advantage of the discrete time representation. Okay, so I think with that I will stop for today's discussion. We will also give you some simple exercises to work with in terms of sequences, looking at how to work with sequences and others. We will give you that. But please do come, start preparing for the next session where we will talk about the basic signals. So in the next session, we will talk about the basic discrete time signals. Okay, we will talk about operations on discrete time signals, shifting, flipping, all of those operations that you can perform, operations performed on discrete time signals. We will then also move on to discrete time systems. Okay, and then input-output relations of discrete time systems. Okay, so this would be our next module of study, and this will open up for us a very rich set of tools that we can start to develop and we can work with in the context of discrete time signals. So with that, let me stop and request you to review some of these basic material, and then we will pick it up in the next session. Thank you.